I'm going to give a very short introduction to the idea what do you mean by mathematical modeling. So for mathematical modeling, the basic task is to design a model related to any realistic problem. Okay, Acha. This designing a mathematical model is referred to as simulation of a mathematical model. For suppose, just take a very simple example of a coin toss. Suppose a coin is there, an unbiased coin is there, and you are just tossing it, say 5 number of times. Okay, so once you toss it in a 5 number of times, you have to set the task to collect the outputs, whether it is occurring head or occurring tail. Suppose if I do that, or anyone who is tossing the coin do that, what he will get? He or she will get any sequence of 5, 0 and 1 binary sequence. It will be obtained once a coin is tossed 5 times. Again, if you toss the coin 25 times, then a 25 length binary sequence will be obtained like this. Now think that a coin is tossed many number of times. So one who is tossing the coin is performing the real life experiment and collecting the data set. So here in the data set is say D1. Okay, and 0 suppose refers to occurrence of head and 1 occurrence of tail. Okay, now suppose another person do not have any coin, but he is assigned with a task. He has what here the computing machine, and he is assigned with the tasks to design a model or to design a just consider a model such that he is going to, or his model is going to replicate the data set, or at least another data set D2, which is approximately equal to D1. That means what? There is a computing machine, okay, which will just generate a data set D2 which is approximately equal to the data set D1. That means what? In this machine, when it is generating this data set D2 for the data set D2, no coin is actually tossed. Instead, what is used? An algorithm is used, which will be just generating this data set, and then once this data set is generated, okay, it will be checked whether this data set D2 is matching with the real life situation, that is tossing a coin with a specified accuracy or not. If it is just satisfying this specified accuracy, then we say okay, the model we have just set into is matching with the real life situation of tossing the coin. This I have given a very simple example. This is not the case always. In any real life complicated situation, I am just trying to say this thing in real life situation we perform the experiment and we get a data set. But on the other hand, it may happen we do not perform the experiment in reality. Okay, we are just setting up a model which will give the observations or the outputs which are approximately equal to that which one should receive while performing the real life experiment. So that is the thing. Say there is a realistic problem. So once I perform the realistic problem, so suppose an experiment you are performing, such as I already said for tossing a coin, then what you get, a data set is generated, okay, in the related experiment. Now the task in simulator means the model which is been simulated. Okay, so suppose there is a computing machine, okay, where some input is given and some output is obtained. Okay, so to design a toy model related to the problem, so whatever problem we consider for which D1 is obtained, we design a toy model such that another data set D2 is generated with the fact that D1 is approximately equal to D2, and this approximation lies within the specified range of accuracy. Okay, now in some cases it is the case that the real life situation problem is so much complicated that it cannot be performed completely at all. Instead, some informations are possible, or some informations can be gathered at most. Okay, but there also, suppose there is a machine and we just input some input, we just give some input in the machine and we design a algorithm, okay, such that from the model which is designed, a data set is generated. Once the data set is generated, it is checked or verified with all the information which we gather from the realistic problem matches with the data set which is produced by the computing machine. If it matches, then that model which is designed is compatible with the real life situation, and you can easily understand here the problem cannot be tackled at all in real life situation. Okay, but via some virtual platform we are giving a data set, we are at least able to generate a data set which is matching with the all the partial information given in the real life situation or the realistic problem concerned. Okay, so here lies the utility of the mathematical modeling. That means using the whatever the theory is, whatever the with the help of the computing machine, an algorithm is generated. Obviously, we will be generating a data set so as to check the data set is just tallying or compatible with the realistic situation problem or not. Okay. So basically this is a schematic diagram of what I mean as a model. So it is just like I am just writing a box here. Just for the timing, you just consider there is a box, and here you are giving some inputs and getting some outputs. So at the very outskirt, that means very roughly speaking, the model is just this thing. Okay. So some inputs are provided and some outputs are given out. So if I do not know what is going inside this box, so if I treat this one as a black box, I do not know. So suppose I have not designed this box. Okay, suppose there are some switches, you are just clicking the switches and you are getting some outputs. This can be considered as a model, but inside the working of the model is absolutely unknown to me. In that case, it is said to be a black box. Now suppose I have designed the model. If I have designed the model, then inside the black box, it no longer remains black box. Okay, this model, that is the inner working of this box, are designed by me. So this designed by me means what? I have set up what? I have set up an algorithm, which is said to be, or more commonly known as, simulation algorithm. Okay, because it is just generating or simulating data. Okay, so once I try to give this algorithm or set up this algorithm, okay, what I need some parameters related to the problem I want to tackle. Okay, suppose I want to tackle or I want to generate an algorithm which is compatible with coin tossing, or I want to give an algorithm which is compatible with dice throwing, or I want to give an algorithm which is compatible with to trace the curve of any particle moving under central force. Just like that I am saying roughly. Okay, so I need the parameters to be used in the algorithm. Okay, acha. These parameters can be some of the inputs and also some of the other than inputs, depending on the problem which is provided. Okay, acha. Then what I have to do? I have to set up some rules. Okay, so as to maintain the logical flow. This is obvious. We know this in algorithm whenever we design an algorithm. So suppose whenever you do a C programming also. Suppose you just set up a C programming to find out the solution of an algebraic equation only. So you set up, you just write down a code. That code is the algorithm. So what do you do in the code? Depending on if I want to find out the root of an equation, we set up all the logical flow in a proper way. So that is the thing I am saying here. Okay. Now once I do this algorithm, then what I do, I set up in a computing machine. For example, in a computer, which is preloaded with a software, compatible software, which will run this algorithm. Okay. Suppose you just only write in English script and you give it in the computer cannot understand it. It has to be given in its own language. That means we need a software. For example, the C programming software we are using. Suppose. Okay. So once everything is set, the software will run this algorithm and ultimately it will give out a data set. The data set D2 is obtained. Okay. Then once D2 is obtained, we verify it with D1. Okay. And once it is verifying with D1 means D1 is already obtained in the real life situation. Okay. Then we verify D2 with D1. If D2 is matching with D1 up to the specified degree of accuracy, then okay, this model whatever I have designed is working with the situation or realistic problem I am trying to tackle. Okay, so this is in short what we mean by modeling, mathematical modeling in short. Okay, acha. Now for up to our syllabus, the Monte Carlo simulation model is a very well-known example of mathematical modeling. Okay, but to be at the very beginning, I just want to say that this Monte Carlo simulation model is a probabilistic model. Okay. So what do we mean by the probabilistic model or the deterministic model here? So suppose a scale is given to you. Okay, a scale is given to you. My task is to measure the length of the scale. Okay, so one time I measured, I got the length say 5 centimeter. Okay, and now I assume that no external force is acting on the scale, no change is occurring in the scale. Okay, then no matter how many times you measure, you will get 5 centimeter. So that is a deterministic event. Each and every time you do perform the task, you are going to get the same output. So that is a deterministic event or an event with deterministic behavior. Okay, there is no uncertainty in it. But now suppose I consider that I have a coin, an unbiased coin, and I have no other information about the coin. What is the radius of the coin, and when once I click it or throw it, how, with what velocity it will just rotate. I have no information. So in under such circumstances, when you go on tossing a coin, suppose you first toss a coin, you get a head. In the next toss, you can get a head or get a tail. So until and unless you toss the coin, you cannot say what you will get. So there is an uncertainty attached with it. So it is an uncertain event or an event of indeterministic behavior. Okay. So actually, whenever we talk about any event I am talking about, or experiment or real life situation, it is of two types. One is deterministic or certain, as I gave the example of measuring the length of a rod, and another is indeterministic or uncertain or probabilistic, whatever you may say, such as the example of tossing a coin. Provided you have no other extra information about the dimensions of the coin or the motion of the coin, you do not have any idea about that. Once that is the thing, then it is said to be indeterministic. Or similarly, you can take the example of throwing a dice also. Okay. Now, whenever we consider any real life situation, either it is a deterministic or indeterministic, or it may be a combination of two, some of the part is deterministic and some other part is indeterministic, whatever. So out of these two we are getting. Okay. Now Monte Carlo simulation method is a modeling, okay, which is probabilistic in nature. Okay. So probabilistic in nature means what? It is based on random number generation. When any Monte Carlo simulation is performed, random numbers are used. Okay, because it is probabilistic in nature. And random numbers means what? A real number. Say suppose I consider real number only. Say real line is given. What I am supposed to do? I am supposed to create random or select random numbers from this, or random elements from this real line. Okay. And just as we have discussed before, up to our syllabus, we have discussed two methods for generating random numbers. That means generating a sequence of numbers without any pattern. Okay. So that is, for example, using the linear congruence method or using the least square method, like that. So Monte Carlo simulation is based on this random number generation because it is a probabilistic method. Okay. Exactly how it is, once we use the Monte Carlo simulation method, you will get a very clear idea about it. Okay. For time being, for up to this lecture, you have the idea that as it is a probabilistic method, obviously the intuition is some uncertainty should be attached with it, and for that uncertainty to be attached with it, we need random number generation. So random number generation forms the basic of the Monte Carlo simulation. Okay. Achha. So this is the thing. Achha. So from here the take home message is that it is based on random number generation. Okay. Now some of the advantages. The principal advantage of Monte Carlo simulation is the relative ease with which it can sometimes be used to approximate very complex probabilistic systems. That I already said, very complicated real life situations can be tackled with, if you are able to design a very specific mathematical model. Monte Carlo simulation gives some positive attitude in that respect. Okay. Achha. Additionally, Monte Carlo simulation provides a performance estimation over a wide range of conditions rather than a very restricted range as often required by an analytical model. Okay. That means quite obviously, whenever an analytical model we want to just design, we have to take care of many more restrictions compared to designing a probabilistic model. Some relaxations may be just given, but I again repeat, this depends on the situation, depends on the problem you are dealing with. It is not the case always. I cannot say this in general. Okay. In some cases, obviously, due to the use of Monte Carlo simulation, some relaxations can be taken into consideration compared to whenever we are using any analytical model instead of Monte Carlo. Okay. Achha. Third positive side of Monte Carlo simulation is here that the model has control over the level of detail in simulation. Okay. So for example, a very long time frame can be compressed, or a small time frame may be expanded, giving a great advantage over experimental models. Okay. Also, that means what? It can control a wide range of data, in short. Okay. You can just as they have said, you can expand a given time frame, or a given frame of any quantity you are measuring, or you can likewise compress also a given time frame, or any given frame of reference, or given frame of quantity you are measuring. Okay. Another thing is that you can control a submodel. A particular submodel can be changed rather easily in a Monte Carlo simulation. Okay. So that means what? Whenever we are thinking about the whole model, say this thing, it may be broken into submodels, quite obviously, depending on the level of complication. Okay. So it can be broken up into many, say, submodels, and Monte Carlo simulation in some cases is helpful. Suppose I have divided into 5 submodels, and suddenly after doing third or fourth submodel, I thought, or I just observed that I need to change something, or I need to modify my first submodel to some extent due to some reason. Okay. So if you use Monte Carlo simulation, it has been observed that gives advantage. Suppose that if I now coming to the third step of the model, I need to modify my first step of the model. Suppose, then if I use the Monte Carlo simulation, I can go back here, modify it, and come back without just incurring much change in this model up to third step. Okay. That means I can control a submodel within a model easily compared to other simulation protocols or other simulation models if I use Monte Carlo simulation model. Okay. This I cannot just give very clear idea, because I am just giving out the very rough outer sketch of what we are the positive sides of Monte Carlo simulation. This actually, once we use it in our particular problems, there and there only we will discuss if there is any advantage of using the Monte Carlo simulation. Okay. And the last one is compatibility with the available softwares. As I already said, whenever you are just writing on an algorithm for a very complicated model, you are not going to calculate it with the calculator or by hand. You need a computing machine with high efficiency, such as a computer. Okay. So for that, as I already said, once you write down the algorithm in some English script, computer is not going to understand it, so it has to be converted into the computer's language. So we need an interface. So we need a software. So as I named as a C programming, because we know it up to some extent at least, there are many other programming softwares. Okay. So Monte Carlo simulation method is such that it is compatible with the many of the available softwares. So this is also a very important requirement for any simulation model we are trying to create. Suppose you are trying to give any mathematical in any simulation model which is not at all compatible with some of the efficiency of your computing machine, then it is useless. Suppose I am just giving a very short example. Suppose I am using a computing machine which has can calculate up to or store the data up to 10 to the power 5 units. Okay. But suppose you have generated a model which is giving a data, or rather requiring a data greater than 10 to the power 5 units. So if I now want to use my machine to run the model I have obtained or I have just designed, it is impossible to use my machine because my machine cannot store above this one, 10 to the power 5 units. Okay. So I need to modify my model. Okay. So that is, I think, Monte Carlo simulation is designed in such a way so that with most of the conventional softwares which are available, these are the name of some of the softwares they have mentioned here, you can simply just use it using these softwares. Okay. Achha. Then what? Then let us say some negative sides of this software or Monte Carlo simulation model. Achha. On the negative side, the simulation models are typically expensive to develop and operate. They may require many hours to construct and large amounts of computer time and memory to run. Okay. So that means what? Again, it is related to the efficiency of the computing machine you are using. Monte Carlo simulation is giving them some advantage. Obviously, at the cost of something. The cost is what? It is requiring a large space. So that large data it is simulating, so that it needs, whenever any machine is running this Monte Carlo simulation method, that machine should have a large memory available. Again also large time is required to run the algorithm related with it. Okay. Also, another disadvantage is that the probabilistic nature of simulating model limits the conclusions that can be drawn from a particular run unless a sensitivity analysis is conducted. Okay, so what is the sensitivity analysis? We will just run it in details, greater details once we do this part. Okay, in optimization of modeling or optimization model, we are not going into the details of it now. So the thing is that it is quite obvious. See, once you are just using a probabilistic method, what is the basis of it? Using random numbers. So random numbers mean using a sequence of numbers selected in an unpredictable way. Okay, so how many random numbers you are taking? So suppose I say it is obtained also, and you will see rather once we use the Monte Carlo simulation later in area calculation, in volume calculation, like that. So what is the main thing? See, D1 is obtained in the reality. Okay, and D2 is obtained suppose using simulation model. Okay, so suppose Monte Carlo simulation model you are using. Now Monte Carlo simulation model being a probabilistic model, the number of runs, if you increase, the accuracy is going to increase. It is quite obvious, because if you can just also just match it, because of the say what we when we derive in probability of an event, we have the idea of frequency distribution. If A is a favorable event, how the and n is the total number of events, and say na is the favorable events, okay, compared to or related to A, then how is the probability of the event A is calculated? Pa is equals to na by n, and then we take limit n tends to infinity. That is the frequency definition of probability. So this n tends to infinity means what? If the situation demands you go on increasing the number of trials. N means the total number of events, so you go on increasing the number of trials. That is the requirement, right? So for that, this is coming whenever we are using the probability. That means whenever we are using something uncertainty, as we are trying to match with the exact data, if you try to increase the accuracy, then obviously we have to take more and more data. The number of data, if you increase, suppose for 10 to the power 5 units of data, you are getting some accuracy level up to say 10 to the power minus, suppose minus 2. This accuracy level will be increased, or this accuracy will obviously will be increased if I say suppose instead of just generating 10 to the power 5 units of data, you are now generating 10 to the power 8 units of data. Okay, so this is the thing. So I require, as you can easily see, this will require much more memory, much more time compared to this. And as it is a probabilistic, we need to increase the number of turns or number of trials. So that is the disadvantage for the Monte Carlo simulation method. Okay, another thing, let me just mention it here. That is not only related to Monte Carlo method, that is related to any simulation model I am saying. See, as I said, two things you have to keep in mind. One is the original realistic situation, I write it realistic event. Another is the simulation model. Okay, as I already said, it can be of two types. I write in short D for deterministic and ID for indeterministic. Okay, similarly for simulation model also, this is of two types only, either deterministic or indeterministic. Okay, so the situation is key. Any deterministic realistic event can be generated or can be just supported, or we can just generate a simulating model which is of deterministic nature or maybe of indeterministic nature. So suppose for D, I am taking area calculation under a curve. Suppose I am taking area calculation under a curve. Suppose this is the curve given, very complicated curve. You do not have the idea how to calculate it using the general integration procedure. Suppose, okay, and I have to calculate this much of area. You can use a deterministic procedure. In case you use deterministic procedure, then for the deterministic procedure you can think of any quadrature formula, that is numerical integration you can think of. We will learn numerical integration in our numerical analysis part. So you can use numerical integration to calculate the area. So that is a deterministic procedure. This is also modeling. Okay, so this is a deterministic procedure. DP I am writing. deterministic procedure, that means this thing. Okay, again you can simulate this area by using Monte Carlo simulation method also. But Monte Carlo is a probabilistic method, so in that case you are using an indeterministic method. So see, the real life situation is what? Area calculation. Area calculation is obviously deterministic. No matter how many times you measure the area, you should be getting the same area again and again until and unless I change the curve or I change the initial conditions, this range. Okay. So y equal to fx is given to me. It is not changed, and x range is also not changed. So if these two are not changed, how will the area change? So this is absolutely a deterministic nature problem. Okay, but I can use it, or I can generate it using a deterministic model also or an indeterministic model also. Okay. So how we generate it using Monte Carlo simulation method, that is the topic included in your syllabus. We will discuss it in details afterwards. Okay. Again, if you consider an indeterministic model, say suppose tossing a coin, again it can be generated via a deterministic model or via an indeterministic model. Okay. Again, the same thing we can say ki once already I have said that if I consider the indeterministic, then D and ID both you can just be used to getting this indeterministic method. That means this whole thing connectivity is there. That means suppose I just keep this as two as separate. One is the realistic possibility, another is the virtual possibility. The virtual you may say here. That means you just based on algorithm here. So here deterministic, here indeterministic on this part, and here also deterministic, and here indeterministic on this part for the virtual model. They are connected like this. This thing is a reality. Okay, so with this I have just given you a very rough introduction of what we mean by mathematical modeling here. Okay, so let us stop here.